title of my talk. This is work that I did together with Alfonso Tortorella, who was a postdoc in Leuven and I was in Portugal, and Stefan Goedens, who was a PhD student of Jan Marcus and of mine, and who's now finishing his one-year postdoc in Bonn. So I will try to make the talk as geometric as possible, trying to suppress all the formalism about deformation theory. And so the goal is to give a good parameterization of symplectic foliations nearby a given one, and then draw some geometric consequences from this. And this connects also a bit to Marius's talk, the last talk of the conference, because so I will not talk about the existence question of symplectic foliations, well, of a given rank on a given manifold, but I think Marius will address that on the 5-sphere. So let me start with a little piece of linear algebra, just because I will use it all along. So let's take a vector space. So then we can look at bivector fields. No, sorry, bivectors. So elements of which 2V. And but such things are in bijections with pairs consisting of a subspace of V. S subspace of V. And this subspace has a symplectic form, so to say. So a skew-symmetric bilinear form on S, which is non-degenerate. So this is just linear algebra. How does it go? If I have a bivector pi here, then S is just the image of the contraction with pi, which I will also always denote with this notation. And omega is obtained with inverting pi in some sense. So pi sharp is the contraction map with pi. So actually it goes from like V star to V, but it descends to a map here, which is invertible, and well, up to a sign, the inverse is a map from S to a star, which is contraction with the bilinear form. That's my omega. Okay, so this is just linear algebra. And and this is what explains the following. So now I fix the manifold M. And on the manifold, then we have a bijection between regular Poisson structures, and I hope it's visible. I will call Poisson bivectors always pi, and the symplectic foliation, well, it's a pair. F foliation, so the one given by it's the so-called symplectic foliation associated to the Poisson structure, and omega is a foliated 2 form. I'll write that down explicitly because it's kind of standard. Okay, so let me fix now a regular Poisson structure. Also, I didn't say explicitly what regular means. Well, it means that the sharp map has constant rank, so that's why I get a foliation here and not a singular foliation or something like that. Okay. So I make a choice, which is auxiliary and makes things easier. So I fix a distribution. Complementary to a symplectic foliation F. I call it G. M. And well, for simplicity, let me assume in this talk that it's involutive. So this will make things a bit simpler. So there will be some DGLAs, differential Gredelli algebras, appearing in this talk. If G was not involutive, we would get a null infinity algebra with 3 non-trivial brackets. the first, the second, and the third. So this gets rid of the trinary bracket. And okay, and this chart of G, which I will draw in a second, determines with two form in the manifold, which I will call gamma. So that's the extension of the leaf-wise symplectic form with kernel G. So with kernel G, I had to draw a little picture for this. So we have like this foliation, these are the leaves. So then we have the tangent spaces to the leaves, of course, the distribution. So G is transverse to this. On each leaf we have, well, on the leaves we have the leaf-wise symplectic form omega, and I extend it to a two form on G, on the whole manifold M by requiring that it kills G. Okay, so these were some kind of preliminaries. So now let's deal with this.
What is a sim to be voted?
Sorry?
What is a sim to be voted?
G.
It is important.
So I have a foliation, and I assume, well, essentially I assume that I have another foliation which is transverse to it. That's the assumption.
But it may be only local, or it needs to be global, or
So everything here is global.
including G.
Yeah. So G, what really matters is that G is a distribution transverse to the foliation. So that's all I really need. But I won't assume in this talk that it's involutive. But so that's a strong condition, I realize. But to make things a bit simpler, I want to assume that today. So now parametrizing. Parametrizing what? Parametrizing regular bivector fields and regular Poisson structures nearby pi. Okay, so a little problem, which also makes things interesting, is the following. So regular bivector fields is not in a affine subspace. Of this case of bivector fields. Okay, let me be a tiny bit more precise. So, so I fix from the very beginning a regular Poisson structure. It has a certain rank, right? So the symplectic foliation has a certain. The leaves have a certain dimension. And whenever I say regular bivector field or regular whatever, I always mean of that rank. Fix the rank. And so bivector fields of a fixed rank do not form in general in a affine subspace here. So, well, let's do a little bit more if we want to parameterize them well. And, okay.
Is it because of the Jacobi identity?
No, I wrote bivector field here.
Just any bivector. Okay.
Well, I mean, obviously they're not a linear subspace, right? If you take two bivector fields of rank 4, some it will not have rank 4. But they're also not a affine subspace. Okay. So now this is a subset of multivector fields, which I call good. And well, the motivation for this definition will be apparent in a couple of seconds. So to define this, I just need a foliation. So I can take all the multivector fields with the property that if I contract them with if I contract them with two covectors that annihilate the foliation, I get 0. So I will eventually write this a bit more explicitly, but not right now. Okay. And so this is some subspace of the multivector fields. And the reason why that appears natural is the following. So now I'm trying to get an idea of how so this space of bivector fields of a fixed rank looks like. So let's take a curve of such things. Pi t. So I take a smooth curve of regular, well, let's put in the integrability condition at once. So let's take Poisson structures, which at 0 goes through pi. Okay. So what can we say about the velocity at time 0? And I'll try to write it here. So let's take the velocity d dt at time 0. Well, this is one of these good bivector fields. So the fact that this curve of regular Poisson structures at time 0 is my fixed Poisson structure, regular Poisson structure pi, to symplectic foliation I called f, implies that the velocity at time 0 lies in the subspace. And okay, so that would be true if I said bivector field instead of Poisson structure. Now the Poisson condition, adds something, but it is very well known, namely the fact that the velocity is closed with respect to the Poisson differential.
Pi itself is a good bivector field?
Yes, pi happens to be a good bivector field. It's not important at all, but it's true. Right? So this is well known, like corresponds to the fact that the first Poisson cohomology governs, the second, the deformations of Poisson structures. And so I wanted to. Okay. So regular here corresponds to the fact that I have an f here. Okay,
So this condition that was just above vector. So being in x to f doesn't mean that the subspace induced by the bivector, the subspace of Tm, contains f.
Contains f, no.
For pi to be in xf doesn't mean that image of pi sharp contains f.
So the image of pi sharp is f by definition.
Yeah, but if I have an f given, and if I ask this requirement on pi with respect to f, what does it mean for?
So let me write it down.
It means that at least one leg must be in f. One leg of the two.
Yes, pi cannot have two legs that stick out of f. Just I will write it down in a while. Okay. So anyway, so this makes this bunch of this family of this subspace of bivector fields appears naturally because of this, and so that justifies a bit the definition above. And okay. So the result about parameterization of this regular bivector field, so no Poisson condition at the moment is the following, that if I take, small, that's something I'm not making precise here, good bivector fields, then they correspond bijectively to regular bivector fields. So, small, so they are nearby pi in the sense that the corresponding, distribution is still transverse to G. So, and something that I find a bit interesting is how the parameterization goes exactly. So that's something I'll spell out. And so this Z gamma is the gauge transformation of Z by the two-form gamma. So gamma is the two-form gamma lives on the whole manifold. It's not closed. Its restriction is pulled back to the leaves is closed. Gamma might not be, but still you can talk about gauge transformations. And so let me give a name to this. Well, just call it x of z, like exponential, because it has some nice properties. And now let me try to make a drawing of the situation. So, okay, like the blackboard is the space of bivector fields on M. So somewhere I have my fixed Poisson structure pi. So here I draw the space of good bivector fields. So this is a linear subspace, right? Should go through the origin, but I translate it so that it's based at point pi, and so in the space of regular Poisson structures, regular bivector fields, regular bivector fields look something like this, like a submanifold, so to say, tangent to the subspace, and this map takes a good bivector field Z and maps it to some point, to some regular bivector field. So I really think of it as a kind of exponential map. So this red dot here is x, Z. And okay, let me continue on a different blackboard. So now I want to describe a bit the parameterization as explicitly. I mean, it can be described quite explicitly.
So gamma is this form that you fix from the beginning?
Yes. I mean, so that is determined by the symplectic foliation and my choice of complement G. Here. So remark. So this X thing, this map here, is a submanifold chart, submanifold chart for the space of regular bivector fields, and and its derivative at 0. So if I take the derivative of this map at the origin in this vector space, that's just identity. The identity of the space of good vector fields. So it behaves exactly like I don't know, the exponential map of a Lie group or a Riemannian exponential map. Okay? So as a consequence of this, so if I take one of these good bivector fields, I can always prolong it to a curve of regular bivector fields. And by prolong, I mean that I get a curve of regular bivector fields whose initial velocity is this one. And well, this is the curve. So this is a curve of regular bivector fields through pi with initial velocity z. So it's like this, and the curve looks something like this. Okay, so as long as I don't have the integrability condition, well, things look very nice. So let me make this map explicit. So explicitly, so in this, well, I think addresses one of Marius's questions. So remember that we have the splitting of Tm into two distributions, the tangent bundle into distributions. So wedge 2 of Tm splits into, well, is the direct sum of three components. Here I have only two of them. So these good bivector fields contain only two of them. They don't contain wedge 2 of G. Okay. So in this, this is the same thing as, well, I can think of this as endomorphisms from the dual of this distribution into G. Okay. So now let me take an element Z here, and so I can write it. It will have a component in here that are called ZA, and a component in here that are called ZB. And okay, so how do these two components contribute to this regular bivector field that I construct out of Z? So
The initial velocity, wouldn't it be by that formula z to the power gamma?
no, it's really.
If I put a t in front of z and take the derivative?
No, it's really easy. Okay, I cannot do the computation in my head, but it's really easy. It's not the gamma. Well, I guess one has to see what happens if you take TZ and then apply the gauge transformation.
I see.
So this thing here, well, I'm telling you, is a regular bivector field. How does it look like? So I will write down a couple of forms. Well, okay, I can say how it looks like by specifying, well, the image of this sharp map, which will be a distribution, and then a non-degenerate two-form distribution. Right? That's kind of the analog of saying that regular Poisson structures correspond to symplectic foliations. So the distribution is the following. And I'll try to make a drawing at the same time. So this is a drawing of TPM, sorry, of the TM at some point, some tangent space. Here I have the G part, here I have the tangent space to the leaf. Okay, so the distribution of pi was this one. Well, now I'll get a new distribution. Let me draw it something like this. And, well, so naturally it's the graph of a map from here to here, right? Because it's well, as long as Z is small enough, the distribution will be still transverse to G. And this map, and indeed the distribution is the graph of the following map. So it comes from the second component here. The second component gives me a map from, well, the dual of TF to G, but since, well, since F is a symplectic foliation, I can use the leafwise symplectic structure to transform this, to replace this into TF. So this is the leafwise symplectic structure, then I compose it with CB, there is a stupid minus sign, and this is a map from TF to G, and the graph is, well, is like the new distribution. And what is the leafwise symplectic form here? Sorry, the leafwise two form here. That's where the first component comes in. Well, this, strictly speaking, is a bivector field along F, along the foliation. For the same reason, since I have a foliated symplectic form, I can make this into a two form. Inverting it. So that's what I denote by wedge 2 omega flat. So that's contraction with omega. Okay. And so both these and these are two forms here on TF, but well, I can pull them back to myself. So I'll just write PR star. So the bottom line. So the bottom line is that this component changes the distribution and this the foliated two form. So now I'll state the result when. So up to now I was essentially doing linear algebra, so the Poisson condition was not used. Now I will use it to then state the result. So, and if I have time, I will say a couple of words about the proof of the main result at the end, but I will not do it now. Yeah.
So where does gamma come in the in the right-hand side of that correspondence? As ZB and ZA, the components of Z gamma?
So gamma encodes both this complement G and the leafwise to form omega. So I agree that gamma doesn't appear, in this formula, but G and omega do. So that's how gamma enters. Okay, so this is the main theorem. So there exists a differential graded algebra structure on, so in this case, good multivector fields. Okay, with the degree shift, never mind. And so the differential is the usual Poisson differential, bracketing with pi. And there is a strange bracket, which I will call bracket sub gamma. So this is not the Schouten bracket. So it's some bracket that ends in gamma, and okay, this controlling deformations of pi. And so the map, okay, let me say it orally in the interest of time. So I had a projection, I had it erased between, bivector fields here and regular bivector fields, so that this exponential map. So if I restrict it to Maura-Cartan elements here, so these are bivector fields satisfying the Maura-Cartan equation, which is d of the bivector field plus 1/2 of the bracket of 0, then I get exactly Poisson structures on the other side. So, so this gives me a parameterization of regular Poisson structures nearby pi by element, good bivector fields satisfying this quadratic equation, which is the Maura-Cartan equation.
So this result depends on the choice of G.
Yes.
And if you change G, the two Lie algebras are
quasi-isomorphic. Sorry, L infinity isomorphic. So without quasi, L infinity isomorphic. Yeah. So this is a result of actually Marco Gualtieri and Nicolas and Geoffrey Scott.
Using gamma, you can think of that the complex, just the vector spaces as foliated forms, direct sum foliated forms with values in the conormal bundle.
Yes.
The second one, it's what appears in the formation of foliations alone. So how is d pi then in this direct sum decomposition? On foliated stays foliated. On the ones with values in conormal bundle, there is a differential there, but there is also a component to foliated.
So that's the next thing I wanted to write down, I think. So let me write it down, and maybe that will answer the question. So, to put this a bit in context, so there is a short, exact sequence of strict, DGLA maps. So in the middle, I put this good vector fields. So inside here, there are the multivector fields tangent to the original symplectic formation. And this projects to what Marius was saying. So foliated differential forms with values in the normal bundle, which for me is just this complement G. And okay, so this is a DGLA. This is a DGLA. So this governs the formations of the foliation F that underlies my regular Poisson structure pi. And as we saw, this governs the formations of pi is a regular Poisson structure, and this is just a complex. So with the Poisson differential, this is just a complex. Using the Leuven symplectic form, this is isomorphic. This is isomorphic to the foliated differential forms with the arm differential. And so does this say something about answer your question, or?
Well, my question, I guess, was how non-split is this? So now I see the answer to my question. You see, there is another differential depending on gamma, from the one with coefficients to the one on F. You have to decompose.
Yeah, I don't know. I don't know that.
But still, there is a deformation complex for the foliation, which is, but that you are saying is a DGLA, not a...
So here I'm assuming the G is involutive. That simplifies things. Otherwise, I would have to say cubical infinity algebra. And
on the other hand, there is a huge complex controlling the formation of foliations, which is a DGLA, and the choice you made makes it quasi-isomorphic to that L infinity.
Yes, I think this was. Yeah.
But the big one is nice, and it's above for the foliation. Do you have something like that for?
No, like here. So what you mean to replace this, or which is a quasi-isomorphic, L infinity quasi-isomorphic to this, is the deformation complex of the Lie algebroid TF. This is an evolutive distribution for Lie algebroid. So you can look at Lie algebroids together with Lie algebroid 2 cocycles, and that picture should give something quasi-isomorphic to this, right? Because a Leuven symplectic form at the end is just a non-degenerate. That didn't work. So I wrote this down. To emphasize what? That if you have a deformation of the, we have a strict DGLA map, so that relates the formations of regular Poisson structures and of foliations. And that's to be expected because at the level of Maurer-Cartan elements, so here we have regular Poisson structures, here we have foliations, and it's obvious that if you have a regular Poisson structure, you can take its underlying foliation. That's foliation, right? You have a forgetful map. So this leaves that forgetful map. That's my main point. So now I think I have 15 minutes, and so I can try to write down some geometric consequences, and I will hand wave the proof of the main theorem at the end. Deformations. Okay. So let's take a curve or a smooth curve of Maurer-Cartan. That's what MC means. Elements in this DGLA that I just wrote down. So a path of good bivector fields that satisfies the Maurer-Cartan equation, which goes to the origin, and then what can we say about the velocity? The initial velocity. The initial velocity is close with respect to the Poisson differential. So that's because each of these at time t satisfies the Maurer-Cartan equation, so the velocity, initial velocity satisfies the realized Maurer-Cartan equation, which is given by the Poisson differential. And if you take second derivatives at 0, you see that, so the binary bracket, so this strange binary bracket that I didn't write out explicitly, and well, applied to twice this thing, is exact. So this is so these are facts that are used very often in deformation theory, and so okay, to save time, let me not write down the definition, but say that an element, well, a bivector field that is closed is what I call infinitesimal deformation of pi. So velocities, initial velocities of curves of Maurer-Cartan elements, which we saw correspond to regular Poisson structures, satisfy this condition. So let's call those infinitesimal deformations. So one first, well, okay, and all, so everything that I will say now is not surprising. There is no big surprise. In a way, we just checked that what you expect, what one can expect actually is true. So, okay, so there exists infinitesimal deformations omega pi, which, well, are obstructed. What does it mean? It means that they cannot be prolonged to a curve of regular Poisson structures. So what I'm saying here is that, so if you take a good bivector field, which is close with respect to the Poisson differential, so that's a candidate to the velocity of some path of regular Poisson structures. Well, it is not always the initial velocity of a path of Poisson structures, of regular Poisson structures. So this is not surprising, because if it came from a path of regular Poisson structures, you would have this condition here, exactness. So okay, so geometrically this means that the space of regular Poisson structures is, well, not smooth at pi. So that's a very vague notion, sorry. But so we have a tangent vector. Well, we have an element of the formal tangent space to the space of regular Poisson structures, which does not come from a path. There is some failure of smoothness. Okay, and now I'll make similar statements relating to Poisson structures without any restriction on the rank and to the foliation. So notice that here, so I tried as much as possible to avoid words like obstructed and Maurer-Cartan element and so on. This is really a statement, geometric statement about a curve of regular Poisson structures. And prolongation really means having initial velocity equal to whatever omega w is there. So now I'm writing down the little diagram. So regular Poisson structures. Well, obviously they sit inside the space of all Poisson structures without any constraint on the rank. And also we saw there is a forgetful map to foliations. And okay, so right. Okay. So first I will address this side of the diagram. So remark, which is because it's something that follows easily from what I said. So if a infinitesimal deformation W of pi, sorry, take an infinitesimal deformation W. So if it can be prolonged to to a curve, regular Poisson structures, then the corresponding infinitesimal deformation of the foliation. So I still have it here. Okay, very good. So this map phi is this second surjective strict Dirichlet map, the one that relates to the deformations of foliation. Then this can be prolonged to a curve of foliations, or deforming the underlying symplectic foliation. So this is clear because, well, if you have a curve of monocartan elements here, applying phi, you get the curve of monocartan elements here. So phi preserves structure. So, okay, so proposition, well, okay, let me call it proposition. So the converse does not hold. So meaning that if you have an infinitesimal deformation of pi such that once you project such that the corresponding infinitesimal deformation of the foliation can be prolonged to a curve of foliations, you might not be able to prolong pi.
If phi of W is 0.
In that case, yes. But, so let me get back to this. So what this says is that, well, so there are situations in which you can, so you take your regular structures, pi, so you can deform the underlying foliation in the prescribed direction, but you cannot do it in such a way that the resulting curve of foliations carries Leuven symplectic structures. And, okay. Yeah. So as Nils was saying, so if this is zero in cohomology, then you can. The main reason being that so if you take infinitesimal deformations lying in here, they are always unobstructed. So they don't change the underlying foliation; they just change the Leuven 2 form. So you can always prolong them. Okay. And actually, well, Stefan Credence found lots of nice examples. So there is also an example where like the foliation f underlying my fixed pi has unobstructed deformations in all possible directions. Not only this is unobstructed, all possible directions are unobstructed for the deformation of the foliation, but there is a direction in which the regular Poisson structure cannot be prolonged. And then, so something similar.
So this is on a closed manifold, on an open manifold?
So some examples we have, they're all on compact manifolds. But it's not important. I mean, yeah, I don't think it matters much. The only, in some statements, we assume that the manifold is compact to ensure that vector fields.
These counterexamples that you're saying, that you have examples where you have the foliation can be deformed, but not with symplectic foliation.
So the examples are all compact, I believe.
And that's not important, that the fact that it's compact?
I would say it's not essential, no. The compactness helps, well, to say that if you have a vector field, its flow exists up to time epsilon for some particles.
I guess Rui's question is, take one of your examples. If you remove a point, does it stay as an example?
I don't know, we'd have to think. Right. So 5 minutes, so let me write something similar for this leg, which is actually simpler. It's not. So this is not very surprising, but I would like to interpret this explicitly as I can. The result, which can be prolonged to curve of some structures. But cannot be prolonged to curve of regular so let me try to paraphrase this. So I have my infinitesimal deformation omega. So that's a good bivector field which is closed. So as every good bivector field, I know that I can prolong it to a path of regular bivector fields. Regularity alone is okay. There are examples where you can also prolong it to a curve of Poisson structures. So integrability is also okay. But you cannot do both simultaneously. You cannot get a curve which consists of, well, regular bivector fields which are Poisson. That's what this is saying. Okay, so now I think I have like 4 minutes to sketch the proof. Well, just to give some flavor. So proof of what? So proof of the main theorem, which was the one saying that on the space of this good bivector fields, there is a DGLA structure whose Maurer-Cartan elements parameterize exactly the regular Poisson. So I will not say much because, well, I wanted to focus on other aspects. So let me start with the drawing. So this is a drawing of the Poisson algebroid Tm plus T star m. And, okay, so I'm interested in my regular Poisson structure pi. So let me draw here the graph of pi. So this is a Dirac structure. Right? So I can think of these things as Dirac structure. And now, if you want to deform Dirac structures, well, you'd better choose a complement. And the natural choice would be tangent bundle, but let's make another choice, which is given by G plus G annihilator, where G is the same as earlier. So this is a complement because then, well, taking bundle maps from here to here, you can look at their graph, and their graph will be a direct, well, some sub-bundle nearby. Okay, and
so you're using F plus F annihilator and G plus G annihilator?
I'm not using F plus F annihilator. I wrote only G plus G annihilator.
And this is what's the projection?
Which projection?
The projection you drew with a dotted line?
This is nothing. So that was just to say that any vector bundle map from here to here, by taking the graph, gives me a sub-bundle close to this.
Okay.
So that's a useful tool to study the structures nearby. So Liu, Wanchen, and Xu showed that there exists a DGLA structure on well, this is a Lie algebroid, right? Well, the Dirac structure in particular, Lie algebroid. So on the Lie algebroid differential forms, which governs the deformations of the Dirac structure. So these differential forms of this. So this is my Dirac structure, dual. Well, okay, there is a degree shift, never mind. Okay, let me just write governing deformations of the graph phi as the Dirac structure. So now the graph of pi is canonically isomorphic to just for the projection. So I can transport this DGLA structure on, instead of on this weird thing, on multi-vector fields. And doing this, you get, well, you get the formula that I wrote. Like the differential is the Poisson differential, and the binary bracket is this thing that I call this other sub gamma. And that's a value. So, okay, so now to take care of the regular condition, and so then one checks the linear algebra that Maurer-Cartan elements of there are good bivector fields correspond under the bijection of Leuven to regular Poisson structures. So regular corresponds to the fact that we're looking at good vector fields, and the choice of complement here, well, is what allows to encode the regular Poisson structures by elements that are lying in some linear subspace of this. So the concept of linearity in that linear subspace is exactly what good stable is. And that is it. That's all.
Questions?
Okay.
Yes.
So I have a question about this DGLA. You know that there is a construction when you have an ordinary symplectic manifold and a quaisotropic. There is a construction of a complex of Florian shafts, and I was wondering if this is analogous, but now starting with a super manifold.
So are you referring to the formation of the quaisotropic submanifolds?
Yes.
Maybe the BVF.
Yes, BFV. Yeah. Yes.
Well, so this question, this is a question about the work of Leuven and Shu, basically, right? About whether the formations of Dirac structures can be understood in that way. Well, as you know, Dirac structures are the same thing as, for instance, Lagrangian submanifolds in a certain degree to symplectic manifolds, and so I guess nothing. And actually, I think that Mikhail was thinking about this 2 years ago. I don't know if there has been progress in the meantime. He told me about this a couple of years ago.
Camille?
May you use it to prove rigidity of some foliations? Like the concentric spheres. This one should be a rigid one, I think.
Yeah, I think you knows the answer. So this provides some tools. Yes. So I thought little about rigidity, and complete rigidity up to say isotopies. I think that's very hard to achieve. You might achieve it in some cases, but so even if you have a compact symplectic manifold, you can always rescale the symplectic form to get one that is symplectomorphic to the original one. So maybe rigidity in a sense that is slightly more flexible than up to diffeomorphisms. Maybe one can do something. But I think Janut had some example of honestly rigid Poisson manifold. Is that correct in your thesis?
Also up to some sort of rescaling by Casimirs. I think so.
So the up to is there. It's the first part of your complex, right? That's the B fields. That's the moduli space of Poisson structures, and that's the foliation, right? So if you want rigidity, you would need that thing to be 0.
Yeah, but maybe there are some situations in which this can be controlled.
Can I make a comment related to that? Because we had a beautiful theorem with Rui at some point. He lived for one night, I think, or one day. Because the statement was too strong. It was a rigidity, but the assumption was compact groupoid with 2 connected fibers, which was the same problem with H2 being 0. And there were no examples. But I think here with this complex in the middle, something funny happens, because if you have properness or compactness, there is the problem that Marco is saying, but when you write a long exact sequence in cohomology, there it's 0 on the right, but on the left you need to have an isomorphism of the boundary map, which is the variation of the symplectic form, which is an isomorphism for Poisson manifolds of compact types, for instance. So I think the proof that we had applied to the complex in the middle gives rigidity for Poisson manifolds of compact types, just because one can use the complex in the other case. Sorry?
In the regular case.
In the regular case, yeah. Just making use of the complex in the middle.
Marius, you can always scale by modular Casimir, right?
Yeah, in the,
We have to Casimir, I think.
yeah.
Maybe. So a different question is, can you do the same, but in the opposite case, where the symplectic form is symplectic in the transverse directions?
That's the first thing. Well, that's a project that I carried out with Florian Schatz before this, so this is kind of a dual version. And yeah, so yes.
There is a question in chat. Do you think those obstructed infinitesimal deformation of a symplectic foliation could be realized as velocity vectors of foliations with a twisted Poisson bivector or something similar?
So let me think. I don't know.
Rui, can I give it a second shot about my question about these foliations that you extend and which cannot be symplectic? Is it the failure because the leaves do not admit a non-degenerate two form?
I don't know. Like the tools that we use. So first,
how do you show that this path of foliations does not extend to...
So using the so-called Kuranishi criterion, which I didn't, which has disappeared in the meantime. So it was the statement that if you have an infinitesimal deformation that comes from as the initial velocity of the path, then the bracket with itself is exact, not just close but exact. So if that fails, you cannot extend. So I don't know how to answer. So these are all statements about smooth one parameter families.
I understand.
So,
but that bracket that you just said, right? That bracket would map to zero, right? That obstruction class would map to zero, and so it would be in the first thing, right? So it would be what? It would be a foliated three form.
What would be the foliated three form?
Say you took this obstruction that you just spoke of, right? That's a class in cohomology in the middle complex of what degree? 3?
Yes, 3.
Right, and so, but it must come from the first part of your complex.
Yeah, that's absolutely correct because of exactness. Yeah, so it's a closed tree form. Yeah.
So that means that your fibers must have third cohomology. Is that why you know that the class is non-zero?
I don't know. So we just computed this class, in degree 3, and showed that it's non-zero. So one way to show that it's non-zero is that once you project it, it's non-zero. So because it's easier to work with essentially with the Schouten bracket that you have here.
No, but I think it has to be 0 there because the foliation extends. That's what you're saying.
If the foliation extends, yes, then that is 0 and 1. You have to work.
Okay. Any other remarks or questions?
I'm just curious because you said you mentioned you looked at many examples. So what happens for rib and then for Lawson foliations?
We didn't look at them.
It would be nice to see describe everything there. It may be trivial, but it should be interesting.
No, I agree.
There is also his old work of Melanie Bertelsen, where she looks at foliations and conditions for a foliation to meet a leafwise symplectic form. And so she has some characterization of such she has conditions on foliations that guarantee that there exists a leafwise symplectic form. It would be interesting to see what are the deformations of such foliations, whether that's...
Okay, thank you again for a great talk.